right, let's get started. Thanks everyone for coming. Great turnout. Please make sure your mic is muted. I see a few unmuted folks. We're very excited for this highly requested webinar today that we hope can fuel some of the white papers that'll be coming in soon, and you can get your questions answered and learn some things and see some friendly faces. So with that, I will turn it over to Fred Ogden, the Chief Scientist at the Office of Water Prediction. Thank you for being here, Fred.
Thank you, Zach. Can you hear me okay?
Yep.
Great. Okay, let's get right into this. There's lots to cover. The NOAA NextGen Water Resources Modeling Framework came from a set of commitments that we made with federal water prediction partners. We committed to have a long-term engagement with both the federal water research community and academic communities. We agreed that sharing of models, data, results, and evaluation tools is a good thing. We agreed that use of the framework to partner with other agencies and leverages investments and complementary capabilities to our mutual benefit. We agreed to cooperate and avoid code forks and bifurcations. In other words, all of us committing to use the same standards, essentially. We committed to seek a common architecture that promotes interoperability and reduces duplication of effort, and establish and maintain a glossary of terms used in the NextGen framework. And that actually exists. It just isn't in a condition where we can share it yet. The framework requirements that came out of federal interagencies meetings were that the focus should be on the architecture, not a particular model. So it should be model agnostic. The framework should provide maximum flexibility so as models evolve, the framework can support those changes. We'd like it all to be done in an open source code development method and environment. We'd like a common architecture to promote interoperability and reduce duplication of effort. We'd like to apply standards for coding, coupling data, metadata, model verification, validation, and test data, and tests such as unit tests. And I would say, above all, we would like it to be as friendly as possible to domain scientists and engineers. We'd like to have to rewrite domain science model code only to the minimum extent necessary to comply with the standards. The original author should be able to recognize their domain science code, and that's really important. If it was so complicated to couple a model to this thing that it required someone to go in and rewrite the whole code, the original author can't recognize it and they refuse to work with it. So that's an important need. Another page of requirements, we'd like to use mature open source libraries where appropriate to avoid the use of proprietary or closed source libraries. We want multi-language support, and right now that is C, C++, Fortran, and Python. We'd like the framework to run on hardware from laptops to supercomputers, and all that entails. So checkpointing, hot starting, etc. And we established a 2-week target for a new employee or graduate student with domain science or engineering programming experience to add new water prediction functionality to a model running in the framework. That is a pretty tight target, but in the Summer Institute, we have had students add functionality to a set of models running in the framework in a matter of weeks. So it's definitely doable. We decided with interagency cooperation on 2 standards to support the framework: the basic model interface version 2.0 model coupling standard, which many of you are familiar with, and the Open Geospatial Consortium Water ML 2.0 Part 3 Surface Hydrologic Features or High Features Conceptual Model, as interpreted and applied by a joint NOAA USGS reference hydrofabric team. And that hydrofabric team has done a pretty fantastic job developing tools to work with the hydrofabric. Basic Model Interface 2.0 Model Coupling Standard has some characteristics. BMI compliant models or modules running together in a coordinated fashion remain unaware of each other and never communicate directly. This requires an overarching code that coordinates their execution and exchanges variables between them. I'm going to show you some diagrams. We call this overarching code the NextGen framework, and that is a typo. Sorry. That should say runtime environment, not model engine. The fourth bullet, the BMI standard allows definition of exchange variable name, units, type, and size in terms of, say, dimensionality of an array, et cetera, number of bytes per entry. In addition, the people developing the prototype of the NextGen framework identified the need for a role descriptor, so the runtime environment can identify forcings, parameters, states, et cetera. And that's an important extension, if you will, to the BMI standard. Now, there are a couple of wrinkles with the BMI standard. Because it provides units information, for instance, if it has to transform, if it's coupling two models that use different units for the same quantity, it uses what's called a BMI coupler. And the model engine prototype currently has some built-in couplers to perform certain unit conversions and spatial resampling. A more difficult problem is connecting two models or modules that have dissimilar fluxes, states, or dimensionalities at their interface. That requires developing a BMI mediator that estimates the missing quantities. A mediator is more complex than a coupler because it requires development of domain science code. An example would be coupling 1D channel routing module to a 2D coastal estuary or water body model. In terms of standards-based community engagement, CIROH is essential to this. The recent hydrologic science literature supports development of modeling frameworks as the best way to enable advancements. There have been several attempts at developing a community model, and that just hasn't seemed to get advance things very far. It seems like a framework might be the way to go. CIROH, we currently have over 50 funded research to operations projects, most using the NextGen standards. And then the beautiful thing about the BMI standard and the high features data model is they are, it doesn't, a module that supports those standards is by default in some way compatible with the NextGen framework. The standards really help us there. We have established working groups on meta-modeling programming standards, including enforcement of conservation laws and open source governance. And those discussions are ongoing, and that's part of what I want to talk about today. In terms of community engagement, the U.S. Geological Survey has also selected BMI and high feature standards. So we are in lockstep with them in terms of our standards selection. Other agencies are working towards that. And the CSDMS, or Community Surface Dynamics Modeling System Consortium, developed a BMI, developed standards names, and have considerable experience with model coupling. The framework goals, the next generation water resources modeling framework is not a model. It is a model agnostic, standards-based model interoperability software tool. And the NextGen framework aims to serve as both an easy-to-use community resource for domain science innovations and a hardened operational platform for the Office of Water Prediction. Okay, now I'm going to show you the diagram, which is the overarching high-level 50,000-foot design of the NextGen framework as the vision as it exists now. This is a bit of a Rube Goldberg diagram, and at first glance, it looks too busy to interpret and comprehend. Let me simplify it for you. These numbered things are components that exist unto themselves. And in the concept of software engineering and separation of concerns, they represent one thing, and they do one thing, and they do it well. And they can run standalone, essentially. the order of these objects, the order that the execution proceeds is basically in terms of increasing number. So that's the really course level view. This diagram shows the calibration and evaluation cycle diagram using the NextGen framework. The lowercase letters near the arrowheads, A through U, I think is the how many there are. They show the order in which things happen. The user interacting through most likely a command line interface, or maybe an API if this thing's running in the cloud, possibly a GUI interface, although, you know, its utility diminishes as you go to larger and larger scales with more and more catchments. The user selects options through the runtime environment, says, I want to run this formulation in this catchment using this set of forcing over this period of time, calibrate it using this method, and evaluate that calibration using these metrics. So that's the kind of information the user provides. Now, if you look at lowercase a, I don't know, can you see my cursor when I move it around on the screen?
Yep.
Zach? Okay. So if you look at lowercase a here, the first thing the runtime environment does after it knows what the user wants to do is it reads a model definition file. And I'll talk a little bit about what kind of information that file needs to contain in a moment. Because it needs to know, which models it has available to it in the framework. Once it knows that, it calls this thing that we call a model and data subsetter. Now we have an input library that is massive, and it's getting bigger every day. We have quasi-static inputs, the hydrofabric, which is the high features data model, the national elevation data set, soils maps, you name it. There's thousands of these things that are not updated very often. There are also quasi-dynamic inputs like leaf area index, national land cover data set that are updated, with some frequency. All of those things exist either on a local machine or out on the web somewhere. This data subsetter knows how to get those data. And instead of running the workflow over the entire, either the planet or CONUS, if you're interested, contiguous United States, if you're interested in modeling a few watersheds, you don't want to run your workflows over all of those data. You would like the subsetter to bring a subset of those data that cover your spatial domain and produce a subset, and that's this lowercase d. And once the subset is created over the spatial domain using the maps that each model specified in the model definition file uses for parameter estimation, this thing reports back with this arrow E that I'm done. All right, so the next thing, let's look for an F. Here it is. The runtime environment calls this parameter assignment limits and formatting code. It knows how to run all the model setup workflows for each model that the user wants to run. Now, the model setup workflows are not part of the framework. They come with the model. And when we have to do that because putting them in the framework would make it much more complicated. The framework code is very sophisticated computer science code. And we can't anticipate all of the models that some people want to run in the framework. Someone produces a new model, it will have its own setup workflow code with it. So this component 4 runs these model setup workflows. They read maps from the subset, produce parameter estimates, and write those to the model input stack, this component 5. Now, one of the unique features of the BMI standard is it essentially assumes that each model that you're running reads its own input files. That's why these arrows from 5 go to the models, not to the model engine. Once the model input stack is created, the workflows have been run, there are no errors have been thrown, this parameter assignment limiting and options thing can do two things. One is, optionally, it can write a calibration configuration file. If the user wants to calibrate models, that calibration configuration file would tell an automated calibration routine that would run which methods to run, which metrics to use to estimate parameters, etc. That's optional. If it doesn't do that, it would just report back that to the runtime environment that it's finished, and it would end. So that gets us to lowercase I. After that's done, the model input stack exists. The models are ready to run. The runtime environment J with arrow J creates a realization configuration file that we'll talk about in a moment. And then it calls the model engine, tells it you're going to run, and here's where you find your realization config file. The model engine reads the realization config file with L, and it now knows which models it's going to run, which forcings it's going to use. And this diagram assumes that these forcings data have been pre-processed, and it also assumes that since we're either calibrating a single simulation or evaluating a single simulation or calibrating a set of models, that it's not doing data assimilation. So there is no data assimilation in this diagram. The model engine uses the BMI interface to interact with the forcing engine, which is a piece of code that knows how to read forcings data of some format and provide space-time resampling as necessary for the given models, passes them back to the model engine. The model engine would then pass those forcing variables on to the models that are running in the framework, and that process repeats. The frequency of repeat with the forcing engine could be different than the frequency that it repeats with the model engine, with the models in the library, depending on the desired output interval relative to the interval of the forcings data. Now, the model engine does its thing. It runs the models. It periodically reports a run status back to the runtime environment. So if something goes sideways, if there's a model or a module that's misbehaving, it could tell the runtime environment that something's wrong, and it could stop and not waste a bunch of CPU cycles. Assuming that everything runs correctly for the duration of the simulation, the simulation outputs that have been written during the simulation, it closes those files and it reports back to the run status indicator that the run is finished. So that gets us back through this one. The runtime environment now would call the evaluation manager, passing some information through its command line interface to here's where your simulation outputs are, here's where the evaluation data are, evaluate these metrics using these methods, and it reads the simulation outputs evaluation data with arrow P and produces metrics and could report those metrics back to the runtime environment with this arrow Q. Alternatively, if you're doing this and then the runtime environment could stop if you're not calibrating a model. If you just wanted to test a set of parameters or a set of forcings and see how things did, that would be the end of it. But if you're running this in a calibration loop, this optional arrow Q would write objective values, and those are defined in however you want to define those, multi-objectives, single objectives. Those are then, after that, through arrow Q, the evaluation manager will report back that it's finished. And then with arrow R, the runtime environment will call this automated calibration manager or code. It reads its calibration config. It reads the objective values, and then it applies the methods. You could envision a case where you want to use one calibration method for one model and a different one for a different model. It runs those, estimates new parameters through this arrow T, and When that's finished, it would report back with arrow U that it is done. And now the loop would cycle again with the runtime environment calling this parameter assignment routine, saying, okay, there's a set of new parameters that have been estimated, read them and recreate the model input stack, and let's continue the loop. So that's the Rube Goldberg view of the NextGen framework. And this, as you can see, this is version 17 of this figure. We've been developing it for about 2 years. But each one of these numbered components is a standalone thing that does one thing, with lots of options, of course, but does it well. So it enforces the separation of concerns and testing. I'll go to one more slide here that shows an operational configuration of the forecasting configuration of those same components. This is inside baseball for weather service, but if we're running a national water model using the NextGen framework, this is kind of what it would look like. We've already estimated parameters, so we don't need the calibration components, and we don't need the evaluation components at this point. There would be a script that through a GUI launches the runtime environment. It would read pre-processed forcings data are obtained from other parts of NOAA supercomputing hardware. And then data for data assimilation, stream flow, reservoirs, soil moisture, snow cover, whatever you're assimilating, those come from somewhere else also. And once those are ready through these arrows A and B, then you can run the framework. So that's why C is over here. D reads the model definition file, so it knows which models it's running or what the characteristics are of the models that it can run. I can check that everything's complete and ready to go. The realization config file is written as before. Model engine is run status reported back. Forcing engine gets forcing data for, say, meteorological forcings and for data assimilation. These are data that come in from somewhere else. It interacts through the BMI with the module libraries. Those models read their inputs from the model input stack. And simulation outputs are written. And then there could be a post-processor to produce final outputs. And those would be used in satisfying NOAA's mission. So that's an example of the forecasting configuration of the NextGen framework. Okay, the runtime environment orchestrates execution of all framework functions. The primary frame, and there could be more than one. There could be a simple one that just runs a certain set of modules. There could be a separate runtime environment for operations versus calibration, evaluation, etc. But the primary framework functions, the subsetter, parameter assignments, model engine, evaluation managers, and automated calibration routine, they never communicate or call each other directly. While those objects share information through file exchange or possibly memory, they only communicate directly with the runtime environment. And that enforces separation of concerns, which enhances modularity, reusability, simultaneous development of components, flexibility and scalability, testing, debugging, and readability and maintainability. The model definition file, this is a partial list of what it needs to contain. The name of a model, and you could think of this as probably being a big JSON file. There would be, you need to know what the model name is, what language it's written in. Is the model designed for serialization or checkpointing? What discretization does it use from the BMI standard? Because the framework's model agnostic, it doesn't assume that every model is a square grid model. Some models could be isochrones or unstructured mesh. It's left to the modeler. The list of variables exposed to the framework through the BMI interface, which would include all of the BMI, the name, the units, type, dimensionality, and the role. And some sample roles are explained there. Parameter, calibration parameter, state, forcing, calculated flux, integrated flux, option flag, Boolean, counter, conservation residual, etc. Number 4, the numbering got messed up on this slide. That'll be 6. List of parameter initial values, upper lower limits if you're calibrating. Output interval that the model's designed for. Is it capable of outputting stuff at the time scale of seconds, minutes, hours, or days? And that's important. This information can be used by a model checker to make sure that if somebody's coupling 2 modules, that they're compatible in terms of their time discretization. The optimal duration would be something that I think somebody would like to know. The type of the output interval, is there a minimum or a maximum or no limit? That's important. Required forcing interval with the same options as the previous one. The list of variables that the model exposes to data assimilation, the variable name, the assimilation interval with the same time options, and the processes in terms of the states or fluxes calculated that the model simulates. And we're talking about that in the meta-modeling arena. How do you best come up with a set of those that's inclusive, that allows the framework to identify if a model that's being constructed from components is all of the components are compatible, and that it's complete in terms of complying with some perceptual model of what the user believes are important processes. The hydrofabric tools that have been developed jointly between NOAA and the USGS are pretty amazing. The USGS hydrofabric is focused on points of interest like stream gauging locations. The NOAA hydrofabric aims to promote a more uniform catchment size distribution while eliminating short channel reaches that are present in the NHD plus for computational efficiency in the hydraulic routing. Both of the USGS and NOAA workflows start from what's called the reference hydrofabric, which is derived starting from the NHD plus network that's had a lot of editing done to it to improve it over time. And the hydrofabric tools and their repositories are listed on the next slide. And I don't know, some of you might want to take a screen capture of this. There's a lot of information here, but this shows where the present tools are for manipulating the hydrofabric. Just to check, make sure I'm not talking to myself. Can you still hear me okay, Zach?
Yep, sounds great.
Okay, thank you.
Mm-hmm.
All right, subsetter. Now the subsetter is an interesting bit that uses those hydrofabric manipulation tools. Now the hydrofabric is not just the channels, it's the water bodies, it's the catchments, and it's their connectors, the nexus points. The model and data subsetter, and it is called model and data subsetter for a reason, it allows discrimination of not only spatial domain, but also what numerical model you're going to use to simulate each part of that domain. It needs a config file that would be indexed by hydrofabric element ID. It would contain things like domain identifiers, such as a point of interest or a reach ID, identifies models to run in each catchment, flow path, or water body, a run, start, end, date, time, and seasonality information, because some of the input in the input library is seasonal input. We might want to use time varying leaf area index, for instance. And data set IDs for use in model parameter estimation by model. So for each model that you're going to run, you have to tell it which base maps you're going to use to estimate parameters in the setup workflow. The runtime environment reads the model definition file. It writes a configuration file. It writes a script. Through the command line interface, it calls the model and data subsetter, which then reads and subsets the data from the input library to write the subset, and then it reports back that it's done. Sounds really simple. but there's a lot to it. But a lot of the pieces have been developed, and they're in this GitHub repo. And again, this is probably another great place for a screen cap about the tools that Mike Johnson has developed to work with the model input library to produce subsets for the NextGen framework. The model input library is a component. It represents the user's preferred hydrofabric describing the catchments, flow paths, water bodies, and their connecting nexuses in the simulation domain, plus an expansive library of geospatial data available for use as proxies to estimate model parameters or initial states. The library is segregated into two types of data, and this is an artificial segregation that I think is just important conceptually. They're quasi-static data. These are data that don't change rapidly over most of the domain, or they're not updated regularly. Examples would be National Elevation Data Set. It is updated frequently, but not frequently over the entire domain. The National Land Cover Data Set, we get an update on that every, I think, couple of years. CIROH, again, it doesn't change a lot frequently. And then quasi-dynamic ones, these would be NDVI, leaf area index, things that change pretty quickly. They're observed frequently using remote sensing. It could be remote sensing soil moisture data. All of these things that can affect either model parameters or initial states. The input library. This next slide is, oh, I'm sorry, that slide should be hidden. It's not. Okay, let's look at component 4, the parameter assignment limits and initial state and formatting component. Runtime environment reads the model definition file. It writes a configuration file. It writes a script through a command line interface. It calls this parameter assignments, limits, and formatting code that knows how to run a model setup workflow through a script for each model that is going to be run. And this workflow takes the proxy maps and uses them to assign model parameters. And we'll talk, the next slide, we'll talk about what the configuration file for this component 4 looks like. And depending on whether or not these workflows know how to write outputs to a place where you tell them to, or if they put them in a default location, this component 4 might have to rewrite those or format them in some way to put them into this model input stack. The next slide talks about the configuration file for this component. Since we cannot anticipate the range of existing or new models that might run in the framework, model developers and domain scientists and engineers create model setup workflows. Model setup workflows come with the models. Component 4 requires a configuration file containing all the information needed to run the model setup workflows for each model in the framework in each catchment, flow path, or water body, including catchment ID, path to the input subset, path to the model setup workflow code, map IDs needed by each model setup workflow to estimate parameters and or initial states, command line arguments to launch the workflow with the desired options and inputs, and a path to write model output files to the input stack, which is component 5. So that, I don't think that's an inclusive list, but I think it's a decent start of what we will need for that. The input stack, the BMI standard expects each model to read its own input files. Given that an instance of the NextGen framework running in CONUS will involve running over 1 million distinct model formulations, this represents a great deal of input activity. A particular NextGen configuration will most likely place input files in four different model realizations in different subdirectories of a top-level simulation director. The input stack has several desirable characteristics. Flexibility in format. So hierarchical data structure is one way to do it, but that's going to be slow to read for millions of models. So we might want to use some kind of binary blob that is more amenable to parallel I/O. But I'll leave that to the computer scientists. We'd like it to be extensible, so as models change, that this can change. We'd like it to not fixate on one particular HPC system architecture for parallel I/O. It should be flexible. We'd like to have mechanics for working under the BMI philosophy documented and have it be extensible and flexible. Can I say extensible and flexible enough? 6, the model engine. The model engine is designed around the high features conceptual model. Its object-oriented approach connects the defined hydrofabric data schema to the computational units by the model engine to do the following things: associate model formulations to hydrofabric features, use hydrofabric topology to create computational topology. So if we've got parts of the hydrologic domain that don't communicate with each other hydrologically, they don't need to communicate with themselves computationally either. So it allows you to disintegrate the big problem into small problems that run fast on local hardware on an HPC system without having to use the interconnect. And I'll credit Nels Fraser created this slide. It accumulates, stores, and communicates states. That's what another function the model engine does. It provides input and collects output from model formulations. It facilitates the exchange of data between model formulations. And it manages and synchronizes simulation times and state updates of formulations. Additionally, the model engine supports the integration of model formulations using BMI adapters and the BMI as an application programming interface. The realization configuration file as it exists today is a JSON file. It does a lot of stuff, but one of the things that's really interesting about it is that it allows you to construct a model from components, from modules that just do one thing and do it well. The order in which these process calculators are called, or these modules, depends on the order that they appear in this configuration file. And that's called a multi-BMI formulation. And I see I've got 20 minutes left. I want to get through this done. I want to show this slide. This is the slide showing the current state of the model engine. It takes in analysis of record for calibration, forcing, and uses a lumped preprocessor to pass those to lumped model formulations. It also can take in a kind of a WRF output type CSV forcing file. It runs the formulations through the model engine. It writes out a flow CSV file that is then read by the T-route channel routing code, which uses either gauge data for a simulation, and it incorporates river forecast, center forecast, streamflow forecast data from forecast points, reservoirs, etc., and routes that water and puts it into an HDF5 file. It can also write out a lumped CSV file for each model formulation. That's the current state of the model engine. This is what we perceive the future state of the model engine. And this is one of the things that Raytheon is working on, is going from current state to future state. And this is there's a lot of capability here. Interacting with the runtime environment and the model stack, interacting with the forcing engine, gauge data, RFC reservoir forecasts, doing this S with a circle around it is a spatial regritter functionality, and that has to be used a lot if you're coupling models that use different discretizations or use forcings that have a different discretization than the model does, which is typically the case. There are also some temporal couplers. Say a coastal model might need input more frequently than an hour. So that would be a temporal coupler, as well as probably a mediator in some cases. It writes a lot of output. It also is capable of serializing models and writing out a serialized state for checkpointing or load balancing purposes. I show this not because I want to get into the details of it, but to give you a sense for where we're headed and how complicated that is. The good thing is domain scientists shouldn't have to worry about working with this code. The forcing engine has some user configuration options that I think is maybe too detailed for this discussion. We designed it around the conceptual wharf hydro forcing engine, transformed into a Python basic model interface application with universal regridding capabilities. Its object-oriented approach connects the defined domain structure to a variety of meteorological forcing products, including satellite, numerical weather data, weather prediction models, climate models, and real analysis data sets. The forcings engine includes MPI capabilities to parallelize a given domain regridder for computational efficiency. So it's had a lot of thought put into it. This is the future state of that forcing engine that we envision. And again, if you want to take a screen capture of it and look at it, be my guest, but I'm going to change slides here. The module library supports C, C++, Fortran, Python. It's implemented as it's compiled into a shared library or implemented as a Python module. The module library for the coastal coupling code looks like that. If you want to take a screenshot, be my guest. And we'll make these slides available as well. The evaluation manager we have a kind of a draft of it, but ultimately it interacts with the runtime environment through scripts and an evaluation configuration run by a command line interface. It could have an API that makes it behave like the water resources evaluation service that we support presently. It interacts with Python modules or shared library, just like the model engine does, to do different evaluations of time series data or gridded data. We want this thing to be able to evaluate gridded outputs of models. We'd also like to be able to evaluate forcings data. The evaluation configuration file for this would contain information about the path to the source and format of the simulation and evaluation data, which evaluations to perform when and where, desired evaluations and metrics, how to calculate objective functions if we're calibrating models, and other things. And we're almost done. The automated model calibration future state, as we see it, the runtime environment writes a calibration config file, says we're going to calibrate these models and these catchments using these metrics and these methods for estimated parameters. And right now we have 3 methods in our calibration library: dynamically dimension search, which is a heuristic method, particle swarm optimization, and gray wolf optimization. And we're finding that different models like different methods sometimes better. This thing reads the objective functions that come out of the evaluation manager and produces new parameter values after reading the limits of the parameters here, and writes those out in a format that this parameter assignment scheme can repopulate the input stack. And I believe that's it. Should have put my email up on there. I borrowed this slide deck. I'd be happy to take questions. We've got about 15 minutes, which is about how much time I wanted to have left.
That was great and perfect timing.
Okay.
Thank you, Fred. Let's see who's got questions. I'll moderate.
A disclaimer, we don't have all the answers. We have a lot more questions than we have answers at this point. So ideas welcome. There's
Go ahead
something
and
in the
put
chat.
in chat or use the raise hand feature.
Did I put everyone to sleep?
Someone asked if you can share this PowerPoint. I don't know if we'll share the PowerPoint, but we'll be sharing the recording of this presentation on the CIROH YouTube channel tomorrow.
Oh, that's great.
Go ahead, Ethan.
Hey, Fred, Ethan Kuhn.
Great.
Question for you about lumping these. So let's imagine that, you've got this high fabric setup, right? That's sort of identifying each of the different components and also, crossing that with explicit spatial locations of each of these and so on. As you start to think about like lumping some of these, a model might provide more than one of them, and then having to like disaggregate and aggregate as you're moving data back and forth to those different models. Is that something that like has to be built into the fabric? Is that something that is built into the remapping structure? Like how does that kind of, lifting multiple domains to work together work?
As you saw in the future state model engine diagram, there's a lot of use of spatial couplers there for regridding. And I think at present they're working with the ESMF regridder for that functionality. We haven't gotten to the point where we've been able to evaluate the overhead associated with that. I mean, it might turn out that it's too expensive and we need to do more pre-processing of our forcing data for different models and different catchments.
But like, is there an intent to have the ability to do things like say, I'm going to have a model that represents more than one of these nodes in the fabric, and I can sort of go to the coupler and say, hey, give me information at each of these nodes, and maybe that information is provided by a bunch of different models. There is sort of the intent to be able to like aggregate multiple streams of data to turn them into one stream to hand them off to a model that's going to deal with multiple things.
One of our principles is don't stop somebody from doing something they want to do.
Fair enough. Yeah.
So
okay.
I hope not. I hope we can do what we want to do.
Right. Thanks.
Thank you. Felipe, you're next on my board.
Okay. Hi, Fred. Thank you for that great presentation. I know that there is a lot of thinking and design on those slides. One quick question for those of us working on bringing our models to BMI compliant and being able to be compatible with this framework. Can you think of unit tests or tests that should be run through those implementations so that we can be sure that this will be compatible with the framework when it's available?
So there's a CIROH working group that I think Martin plans to follow up with. We're trying to answer questions like that.
Mm-hmm.
There are many questions like that regarding coding standards, how you develop a model or module that is maximally compatible with the notions of the framework.
Mm-hmm.
And that's a work in progress right now.
Okay.
I think there's an opportunity, hopefully, for interested folks to talk about that and get involved at AGU.
Okay, sounds good. Thank you.
Let's go to the chat and then we'll come back to the hand raise.
Okay.
Pin asks, is there a place that we can find all the available BMI compatible models in the NextGen?
Yes, and on the OWP GitHub page. Although all of the modules we've produced so far are there. Vita, you're next.
Yes, yeah, thank you. Thank you very much, Fred, for the presentation. Looks very complicated, but that's not what I wanted to say. By the way, can you stop sharing, so it would be nice
sure.
to see your face, so.
Stop sharing.
All right. So in the forecasting operational version, you acknowledge data assimilation, so possibility for data assimilation. But you didn't say much about the potential methods. And as you know, there is more than one way of doing that. So do you envision populating the system with different data assimilation method, just like many different models and inputs and all sorts of options all over the place? So same for data assimilation?
Yes.
Okay, all right.
It's model agnostic, and actually I don't care what model people use. I don't care what data assimilation method they use. I want to use the one that works the best.
Okay, and so then since I have the floor, so and who will be determining like what's best? Because it's a big country, I think I asked you that question, before, and it's like the number of possibilities here in this framework is endless.
Well, in an ideal world, a researcher comes with a paper that says that we developed this new scheme and we find that it works really well here. Then OWP or its contractors or designates will test it and say, yeah, actually works really well. Let's use it.
Okay. Okay. So that process of identifying what's best and then the operational implementation or use of that will take a while, right?
Yeah.
Yeah.
Yes. Our null hypothesis is the CFE model, which is basically all of the important bits of current national water model. That's what we're comparing against. If something does better than outperforms that in a particular place, then we have a reason to change.
Okay. Yeah. No, thank you again, Fred. Good job.
Thank you. Anything else? Anything in the chat? We have 7 more minutes. You can torture me for 7 more minutes.
Abakar, I see you're unmuted, so I'm sure something's brewing.
Yes, Fred, I'm trying to figure out, kind of follow up from Vitek's question. I'm going to keep it simple. Let's say I have a basic unsaturated flow model, like a Garner model versus Van Gunington. Now, I could claim that my Van Gunington worked great, but depending upon the condition, it'll be completely different. So, who would see? Such a complicated system, it appears to me. Would it be an agency which will take care of that? Yeah, we'll go with this or go with that, or even solvers for that matter, right? Some conditions, certain things work. Some conditions, certain things work. And the follow-up question is, playing with unsaturated flow, things fail. Like everything runs finally well, and somebody messed up with some parameter, and the whole thing crashes essentially. At least my code crashes. When that happens, how does this big system manage that?
So reliability is, well, so first of all, operational concerns are inherently government function. You guys don't have to worry about that.
Okay.
If we try your model and it crashes, we're not going to use it. We have, we run things for multi-decades, and if it's not reliable, we can't use it.
Okay.
But I think, if you take a step back and say, I developed a BMI module for just vadosome processes. Now I want to test it with other approximations of the hydrologic cycle. The framework will allow that in a pretty straightforward way, I think. We've done a lot of that kind of mix and match testing with different ways of calculating stuff, and it is actually pretty cool for that.
Okay.
Thanks. Any other questions? I know Ethan looks like he has a question.
Marty Clark.
I'll let Martin go. Yeah.
Okay.
Yeah, Fred, that was good. That was excellent. And when you talked about the future state in some of the slides, am I correct in assuming that that's what Raytheon is working on?
Correct. We presented these future state slides to them. We actually presented current state and future state to give them an idea of where we think they should go.
Okay. Yeah. And is there a timeline associated with that?
They are supposed to, at the end of, I think, the end of FY24, produce a usable system that has a certain degree of functionality, not total functionality.
Mm-hmm.
So the project's very front loaded.
Right. Okay. Very good. Thanks.
The other thing that I think is really interesting, Martin, is that I don't think we have to wait for them. Our prototype is actually moderately functional in terms of its feature set. And if you're developing BMI compliant modules and you develop your own driver program, you're still fundamentally compatible with what we're going to produce.
Yeah, thanks.
Right. Thanks, Martin.
Yeah, thanks.
So you want to say anything about, your thoughts about what we might be able to do at AGU regarding discussions on modeling standards and that kind of thing?
Yeah, so there's the think tank on building models from modules. We had an abbreviated meeting at the CIROH Science meeting back in September. It was abbreviated because of the looming government shutdown that didn't happen, so we had to modify that a little bit. That group broke up into three tiger teams, if we can call them that. The first tiger team was on perceptual models, and they met a couple of weeks ago. And Jonathan Frame was leading that, and he's provided a nice Google Doc that's got some information in it. The next one is being led by Nels Fraser, and so that group's going to be meeting next Friday, and that's going to be talking about some of the coupling standards that related to Philippe's question. And then the final group is being led by Dave Tarbot, I know I see here, and that's more on the metamodeling aspect, and that group will also meet before AGU. The intent was to come together at AGU. I've been looking at venues, and San Francisco is quite a complicated place, to bring people together. So Fred, I should circle back with you after this to talk about, what's possible. When I was looking at the schedule, that Monday lunch could be, the best time to get together, but we should circle back and see what we can do.
And I would suggest that if you're interested in joining or participating in one of those groups, or at least just listening in on what they're talking about, contact one of those three people as appropriate, and ask if you can be included in the communications. I think the more the merrier.
Yeah, no, I'd agree with that. And or just send a direct message to me, and I'll add you to the calendar invites. Yeah, thanks for that.
I wish I could be involved in those directly, but we've been working at breakneck pace trying to get Raytheon spun up here.
Let's take Ethan's question, and then we have two in the chat, and then I'm going to cut it off so we keep Fred's time valuable.
Yeah, sure. So this is, I guess, more of an observation than a question. I'm really interested as these start to get, this is sort of piggybacking on what Prabhakar mentioned, right? As these start to get more complex and the combinations of models start to be more complex, there's going to be a lot of interesting emergent problems that show up in coupling of it's easy to unit test your own component. It's harder to test, multiple components in combination. Mm-hmm. And it's easy to evaluate a single model, but it's hard to evaluate, multiple models when you start using one model outside of the regime in which it was trained or built or calibrated. So it'll just be, this is just, like I said, not really a question. It's just going to be a challenging problem to evaluate and sort of compare models when you get into this sort of many complex combinations with potential local connections and so on. So I'm excited to see where it goes. It's cool.
I agree. It's going to be a real challenge. I think the challenge is going to be people, not releasing formulations for prime time before they're ready.
All right, we've got three questions in the chat, and one of them is a two-part question. We'll start with the current calibration package. Does it work together with the rest of the system?
Jia Feng, she's our calibration expert. She's developed basically her own framework for doing model calibration. And the components, she doesn't have the separation of concerns like we've elucidated in the high-level design. Things are a bit more tightly coupled. So we talk about the current calibration package. That's what we have, and her tools are actually on the GitHub repo. So what I showed as the future state doesn't exist yet. I hope that answered your question.
Next up, we have, will the NextGen be running at the Kona scale, be calibrated? Part two, what are the challenges you see by calibrating with more than 1 million different modules? Well,
so we have a funded CIROH project. Hillary McMillan is leading, trying to identify hydro regions. Can you use hydrologic signatures to identify likely storm flow generation mechanisms? And can that point us to potential appropriate model formulations? We expect that, hydro regions, aridity index is a really good first cut indicator, but we're going to be doing calibration on a regional basis. I don't think we'd do calibration CONUS-wide. One of the advantages of using simpler model formulations that maybe imply more lumped conceptual components is their runtimes are not so punitive. They're not expensive to run. So doing calibration of simpler models on regions should produce significant, runtime advantages that help calibration.
Our final question. Thank you, Fred. Would the framework allow ensembling using different models / schemes in addition to use of different meteorological forcings?
Absolutely. That's one of the things that we included in our our discussions with Raytheon, that it's highly likely that the best model for predicting floods is not going to be the best model for predicting low flows during droughts. So it would be that's a really easy case where you could say that it might make sense, if a region's undergoing a drought, to run more than one model formulation.
All right, we do have more questions coming in the chat, but I think I'm going to let you get to your vacation time now.
Well, I have a call here in 3 minutes ago.
All right. Well, thank you again very much.
If anyone has pressing questions, email me. I'll put my email here in the chat. There you go. So I'd be happy to answer emails if you have. And I know some of you have sent me emails recently that I haven't replied to, so sorry. Thank you, everyone. I appreciate the opportunity to present to you today.
Thanks, everybody. This will be up on the YouTube channel tomorrow.